Hello, my name is Phil Hoy. I'm a Field Applications Engineer with Bourns. In this video, I will be demonstrating the use of our latest Bourns Protection Evaluation Board for RS-485 drivers. This is a new evaluation board that enables us to try out different surge protection scenarios for a wide range of RS-485 drivers. The evaluation board itself comes in two parts. The main board holds the protection circuit options and a simple 10-bit parallel in serial out shift register to enable us to generate a transmitted serial test byte complete with start and stop bits. We can select the byte we wish to transmit using the dip switches. The three basic protection options that are provided are the familiar thyristor type protector, which goes under the brand name TISP at Bourns, an electronic resettable fuse option under the TBU brand, and a power resistor based option that enables simple upgrade for those RS-485 drivers with internal surge protection. These protection options can be further enhanced using optional TVS diodes or gas discharge tubes as required. The main board provides connectors to allow the drivers to be connected directly to power supplies and to external circuitry if required, and also a connector to allow interface to the surge generator. There are sockets on the board to allow us to plug in different RS-485 drivers to test against the various protection options. The second board is a PCB which can be separated into individual chip carriers and allows several different RS-485 drivers to be fitted depending on their footprint. Many RS-485 drivers from different manufacturers, but using the same package type, also share the same pinout as a kind of de facto industry standard. So with the footprints on this board, we can cover well over 95% of available drivers. The board can be separated into an individual chip carrier, the customer's chosen RS-485 driver soldered onto it, and connectors soldered onto the reverse side. This chip carrier can then be plugged into the main board according to the protection that you intend to test against.
This unit is the equipment needed to test such a board. This is an ECAT surge generator, which is pretty much an industry standard surge generator. It has the option of installing a number of different modules to test to different surge standards. There are many other surge generator types available, and if you don't already have one in your lab, you are likely to be able to rent one for the purpose of your own testing. Because we are dealing with high voltages, which can be anything up to 6 kilovolts, we need a safety box to keep our own hands away from the devices under test. Then we have the measurement gear itself. The key items here are the oscilloscope and a current coil, which converts currents measured into voltages that can be seen on the scope. Before we do any test work with the surge generator, we need to calibrate its output with the oscilloscope and the current coil. I'm going to do the calibration of the surge generator using the ECAT combination wave surge generator module, because this is the most commonly used for testing RS-485 interfaces against surge. It's called up by the IEC 61000-4-5 standard, for instance. This module will generate a voltage waveform of 1.2 microseconds rise time and 50 microseconds fall time to the half amplitude mark when open circuit, but an 8 microseconds rise time, 20 microseconds fall time current into a dead short. I'm going to select a 2 kilovolt surge output voltage equivalent to a class 3 test, and first we'll test the accuracy of the voltage output. It happens that the voltage is spot on what is required, 2000 volts peak, but if it wasn't, then we could trim the surge generator output until it was where we wanted it to be. Next, we're going to take a look at the current. We have a 2000 volt output of the surge generator, and it has 2 ohms internally, so we should be looking for 1000 amps peak. Measuring the current with the current coil, we discover the current is actually a little low. Once again, we can trim this error out by increasing the output of the surge generator to compensate.
Before we go any further, we're going to take a closer look at the protection circuits. This is the circuit diagram for the TISP-based protection. We can see there is a 40 volt TISP protector on each of the RS-485 wires to ground. the TISP will react to any overvoltage applied to it, causing a dead short to the ground. By this means, it will divert the energy away from the protected component. The option of wire wound resistors is included on the board, as these can be used to limit the peak current into the TISP, thus enhancing the performance of the protection. For most cases, they are not needed, however, and certainly for the testing we will do today, the TISP is more than capable of handling the peak currents on its own. An option exists on the PCB to also mount a gas discharge tube. This would significantly enhance the robustness of the protection for RS-485. It is only necessary in those circumstances where the RS-485 cabling could be exposed to high levels of lightning surge. A good example would be an AISG interface on a cellular radio mast. The option also exists to add a small TVS diode. This would enhance both the ESD performance and the protection against residual voltages that might get past the TISP. The device shown is the ideal device from Bourns for protecting RS-485 from ESD, as it includes a positive 12V TVS and a negative 7V TVS in one small device. Most RS-485 drivers have suitable ESD protection internally, however. This is the TBU-based protection circuit. It consists of Bourns' unique TBU devices. These are fast resettable electronic fuses based on MOSFET technology that block the surge energy from reaching the protected component rather than diverting the energy to ground. The TBU itself is rated to several hundred volts according to the device type, but it needs to be protected from any voltage larger than that, and so we've used a 400V TISP to provide that protection. Overall, this TBU-based circuit protection is very robust. It doesn't just provide protection against surge, it can also protect against inadvertent mains power contact.
Now what I'd like to do is to demonstrate the raw performance of the TISP and TBU protection with no RS-485 driver in place, using a blank chip carrier on the board. Here's the blank chip carrier, and I've set up the scope to measure current into a dead short on the connector, since it's residual current into the protected circuit that we are interested in. We've set up the ECAT to generate the surge we want, which has now been calibrated for 2 kV. I'm going to do the test according to IEC 61000-4-5, which for symmetrical lines like RS-485 suggests that the surge is applied common mode with respect to ground, with 80 ohms in each wire. The surge generator itself only has 2 ohms internally, so I've added the 80 ohm resistance externally in line with the connector wiring between surge generator and mainboard connector. Here's the mainboard all set up, with the blank chip carrier in place in the TISP protection socket, and with the current coil monitoring the current. The surge will be applied through the connector with the inline 80 ohms resistors. Okay, I applied the surge to the TISP protection first, and here you can see the result of that test. The current remaining as a residual during the surge is 5.78 amps peak, and that compares to the 25 amps per wire coming out of the surge generator. The duration of the residual surge is about 0.5 microseconds, which is a lot shorter than the surge generator output duration of almost 30 microseconds. Next, I'm going to apply the surge to the TBU protection. Here's the blank chip carrier in the TBU protection socket as before. The test is set up as for the TISP, with the surge applied through the connector with the inline 80 ohms resistors. And here's the result of that test. In this case, the current as a residual is down to 3.24 amps, and the duration is in the tens of nanoseconds range. So this TBU-based protection is particularly good at reducing the amount of energy reaching the protected circuit.
We've taken a look at the evaluation board, and we can see that with the setup on the board we have good protection using TISP or TBU from Bourns. But is this protection sufficient for a real RS-485 driver? Here we've got an RS-485 driver mounted on a chip carrier, and we're going to apply the same surge to this device and see if the protection is adequate. We're going to start with the TISP protection first.
Keep watching the scope on the right hand side, which will monitor the applied surge, and the LEDs on the board. The red LED shows the signal being put out to the RS-485 port, and the green LED shows the same signal echoing back through the driver. Please wait 12 seconds for the surge generator to charge. You can see that after the surge occurs, the green LED continues to show the echo of the signal put out to line, which means the driver survived this surge test. The TIS protection was indeed adequate. This is the same test setup as before, but with the driver this time protected by the TBU option. Once again, keep an eye on the scope and the LEDs. Please wait 12 seconds for the surge generator to charge. And once again, you can see that the signal through the driver is just fine. This protection also worked great.
That concludes our demonstration. As you can see, the new RS-485 protection evaluation board from Bourns allows you to test the surge protection of any RS-485 driver you may choose with any of 3 basic protection options, ensuring that you arrive at a robust and cost-effective protection solution.